Okay, time for something new. Implicit differentiation. Differentiation just means finding the derivative. So we're going to be finding the derivative of y squared equals x at 4, 2. First thing we often like to do is get ourselves a picture of what's happening. So y squared equals x at the point 4, 2. Find the derivative means we're finding the slope of the tangent. If you were asked to find the derivative of y squared equals x, and I asked you this last week, you would do what you've always done. You would get y completely by itself. That is known as explicit differentiation because you are explicit or obviously finding what y is. So we took the square root of both sides of y equals plus or minus root x. We prefer to write that as plus or minus x to the 1/2. And then the derivative becomes plus or minus 1/2 x to the minus 1/2. We're finding the derivative at the point 4, 2. So after we simplify the derivative, clean it up and make it look nice, we realize that at 4, 2, we're looking at the positive root of x as opposed to the negative root of x. Therefore, the derivative is the positive 1/2 root x. At the point 4, 2, we'll plug in 4 for x. We'll get an answer of the slope of the tangent is 1/4. If you look at the line, the slope of the tangent of this line, 1, 2, 3, 4, so it went over 4 and up 1. So the slope, change in y, change in x, 1/4. So everything looks right. What's new? Nothing yet. I would like to remind you of earlier notation. Y prime, dy dx, both mean the same thing. dy dx comes from change in y over change in x, or delta y over delta x, and that's where dy dx comes from. We're not accustomed to using it very often, but keep in mind it means exactly the same as y prime. We're going to be using it when we do implicit differentiation, and I'll give you a good reason for doing that in a minute. The other thing I'd like you to keep in mind is when we took the derivative, what we really did is take the derivative of both sides of the equation. Derivative of y is y prime, derivative of plus or minus x to the 1/2, plus or minus 1/2 x to the minus 1/2. So we just took the derivative of both sides of the equation. Now, time to do this a different way. Implicit differentiation, finding the derivative in an implied manner, all we're going to do now is take the derivative of both sides of the equation. We're not going to solve for y explicitly. We're going to take the derivative of both sides of the equation with respect to x, which is a little bit difficult to do when there's no x on this side of the equation. That's where the chain rule comes in. Much easier to take the derivative of y squared with respect to y, and then chain that with the derivative of y with respect to x. The end result is we'll end up taking the derivative of y squared with respect to x. Where did that 1 come from? On the right-hand side, we're taking the derivative of x with respect to x, and we know that that derivative is just 1. Taking the derivative of y squared, if y is your variable, we're going to end up with 2y. We're going to keep the dy dx, and we keep the 1. Now, dy dx, we said, is just another way of writing y prime, and that's what we're looking for. This is the entire reason for using dy dx. If we had written down y prime, we might have been tempted to combine it with that y and get something that's completely and utterly wrong. By writing it as dy dx, it is far more obvious that it means the derivative, and then we tend not to lose it in these questions. Your goal now is to get dy dx by itself, so we'll divide both sides by 2y. Now, let's compare this to what we did before. What we did before, explicit differentiation, got y by itself, cleaned it up, took the derivative, and it looks entirely different. We're not worried yet. When we did a lot of the max-min questions, depending on how you set up your variables, you might get something that looked different. It was the end result that mattered. So let's keep going. We're going to find the derivative at the point 4, 2, plugging in y this time instead of x. Look at that, we get the exact same answer. So even though your two derivatives look different because you have done them different ways, your final answer is exactly the same. So let's just review what we did. We started with an equation. We did not bother isolating for y. We took the derivative of both sides of the equation with respect to x. Very difficult to take the derivative of y squared with respect to x, so we brought in the chain rule. We took the derivative of y squared with respect to y because that makes far more sense. Chained that with dy with respect to x, and that gives us the derivative of y squared with respect to x. Derivative of y squared, when y is your variable, is 2y. dy dx is just the derivative, and that kept coming down. Continue on until you get dy dx by itself, and then there's your answer. Let's try a couple of examples. Oh, but wait. Why are we doing this? The reason we're doing this is that sometimes it's much easier to do the derivative without having to get y by itself. This one wasn't bad. Either method is about as difficult as the other. This one, on the other hand, is a little more complicated. We'd have to use the quadratic equation if we were going to get y by itself. For this example, I don't have a clue how to get y by itself. So that's why we need to learn implicit differentiation. Now it's time for some examples. Determine the derivative of the following using implicit differentiation. We have our equation. We're going to take the derivative of both sides of the equation with respect to x. Derivative of x squared with respect to x, derivative of y squared with respect to x, derivative of 25 with respect to x. Derivative of x squared we know. Derivative of y squared, we'll use the chain rule. Derivative of 25 we know. Derivative of x squared is 2x. Derivative of y squared is 2y dy dx. And the derivative of 25 is 0. Our goal, solving for the derivative, we want to get dy dx by itself. We'll start by moving the 2x to the other side, and then dividing both sides of the equation by 2y. Clean this up as much as possible. The 2's are common, divide by those, and we get a nice clean answer. Unlike the other question that we did, there's no number in our answer. We didn't finish with 1/4 like we did before, and that's because we're simply not finding the derivative at a point, we're just finding the general derivative. Your turn. Derivative of x cubed plus y cubed equals 8. If you think you know what you're doing, put me on pause, try this yourself, and then get the video to continue and see if you did it right. For those who want to work along with me, let's keep going. I'm going to take the derivative of both sides of the equation. Take the derivative of x cubed, the derivative of y cubed, and the derivative of 8. We're taking the derivative with respect to x. We know the derivative of x cubed. The derivative of y cubed, we'll do a chain rule. Do it with respect to y first, then multiply by dy dx. And the derivative of 8, we already know. Derivative of x cubed is 3x squared. Derivative of y cubed, 3y squared chained with dy dx. And the derivative of 8 is 0. Your goal is to get dy dx by itself. We'll bring the 3x squared to the other side, and then divide both sides by 3y squared. Clean this up as much as possible, and we have a nice simple derivative. Again, what we're finding is the slope of the tangent line. So if you were to graph x cubed plus y cubed equal 8, you could find the slope of the tangent line to that graph at any point by plugging in to the derivative. 2 more examples. X squared plus 2xy plus y squared equals 10. Take the derivative of both sides. The derivative of x squared we know. 2xy, be careful here, this is a product. We'll need to use the product rule. Derivative of first times second, first times derivative of second. Derivative of y squared, you'll use the chain rule. And derivative of 10, we already know. Derivative of x squared, derivative of 2xy, derivative of y squared, derivative of 10. Derivative of x squared is 2x. The product rule, derivative of the first times the second, that's where the 2y comes from. The first times the derivative of the second, the first being 2x, and the derivative of the second being dy dx. Derivative of y squared, we've seen that a few times now. Derivative of y squared is 2y, and that gets chained with dy dx. The derivative of 10 is just 0. There's more than one dy dx in this equation. Our goal is to get dy dx by itself, so we'll take the 2x and the 2y to the other side of the equation. Then we're going to pull the dy dx out by factoring. dy dx is multiplied by 2x and 2y. And now we can divide both sides by 2x plus 2y. Cleaning this up, one thing you might notice, every term has a 2 in it, so we could certainly make the number smaller. Also look for the fact that there's a common factor, there's a negative that's common. If we pull that out, that reveals an x plus y that's common to top and bottom. Slope of the tangent then is -1. That means wherever you are on this curve, the slope of your tangent will always be -1. You might want to graph that just to see what's going on. Last one. This one you should really try on your own first. Please put me on pause. Then check your answer. We're going to start by taking the derivative of both sides with respect to x. Derivative of x cubed, we know. Derivative of y cubed, we need a chain rule. Derivative of 4xy, we need a product rule. The derivative of x cubed is 3x squared. Derivative of y cubed, take that with respect to y first and get 3y squared. Chain it with dy dx. The product rule, the first is 4x, derivative of the first times the second, plus the first times the derivative of the second. The goal again is to get dy dx by itself. So all the terms with dy dx we're going to put on one side of the equation. Move everything else to the other side. Does it matter which side you pick? No. I tend to pick the side that'll give me the least number of negative signs. In this case, it doesn't matter. Now to get dy dx by itself, we'll factor it. It's multiplied by 3y squared minus 4x. We can then divide both sides by 3y squared minus 4x. Beautiful answer. I don't think we can clean it up at all. Now, what if you get an answer of 3x squared minus 4y over 4x minus 3y squared? Compare the two answers. It turns out, although they don't look the same, they are exactly the same. Imagine multiplying the top of the equation, 4y minus 3x squared by -1, and the bottom of the equation, or the fraction, 3y squared minus 4x by -1, and you'd get the other answer. 4y by -1 minus 3x squared by -1, 3y squared by -1 minus 4x by -1. And if we multiply by -1 over -1, we really multiply by 1. So these equations are exactly the same. Be careful when you do the questions. You'll check your answer. You'll look at them and say, oh, wait a minute, they're different. But check, are they really the same? Just look at them. So all that happened for the people who got this answer is when I moved my dy dx to the left-hand side, you moved yours to the right-hand side. And that just meant all your signs were the opposite of mine. Okay, you have homework to do. You can find it in the package. Have fun. Let me know if you have questions.